We completed our discussion on the first part of the refinement proof related to guard strengthening. And let's now move on to the second part about invariant preservation. And you will find the idea about proving invariant preservation in the context of a refinement model very similar to what we did before when we only have the initial abstract model. And the only difference is we have to make sure we put the concrete invariance in the pre-states in the hypothesis, and also the concrete invariance in the post-states in the goal. That's something we have to make sure. That's the only difference. Let's take a look. Right, so this will be the proof obligation rule. Right, I'm gonna go over to iPad to do the usual illustration, but I want to draw your attention to the following. The hypothesis over here is exactly to the first part when we spoke about earlier. You can definitely go back to compare the proof obligation. So we have to mention about the axiom, the abstract invariance, the concrete invariance in the pre-states, and also the concrete guard for the events, right? And in the case of the first part of the refinement proof related to guard strengthening, we have to put the abstract guard. That's what we had to do. But now our purpose is for invariant preservation. That's why we simply put a single concrete invariant condition over here, and we want to make sure the effects for the abstract events and also the effects for the concrete events are actually in place whenever applicable. That's basically the idea. Right, let's now take a look at how we can formulate the sequence related to invariant preservation. And the first question to really ask is about how many sequences do we need in total for the refinement proof related to the invariant preservation. So the answer will be similar to what we did it before, right? We said in the case of the abstract model, when we only got the model without the notion of the refinements, the number of events multiplied by the number of invariant conditions. But that's basically what we had to do. And now you can see the index over here is for the concrete invariance. Let me just put the notes over here, right? You can see the J of I over here. This is basically a single concrete invariance condition. A single concrete invariance condition. A single one. And in this case, we got, how many conditions do we got? We actually got 5 invariant conditions over here for the concrete invariance. So that's why we need 5 multiplied by the number of concrete invariants. How many concrete invariants do we have? We have 2. ML out and also ML in. So that means we got 2 times 5. We got 10 in total, right? So these will be the 10 sequences that we have to formulate and to prove. And for the lecture, I will just try to help you formulate 2 of them, and then the rest of the 8 sequence to be formulated, it will be up to you as an exercise, right? So if you go back to the slides over here, you can see the formula is really about the number of concrete events multiplied by the concrete number of concrete invariants, as I just mentioned. Okay, so we got 10 in total. Right, and just write it down over here. So it will be basically the number of, actually, let me just write down the math directly. Number of concrete events multiplied by the number of concrete invariants. It will be 10. Right, so we got 10 sequences in total to be formulated and proved completely. But for now, we only talk about 2 of them. Right? So the 2 of them I will actually formulate will be the first one. Let me write down the name, which followed the same naming convention. Let's say we talk about ML out, and then which concrete invariant do we want in the goal? Let's say we want invariant number 4 over here. Right? So I'm gonna put invariance 1 and 4 over here. And we're talking about invariant preservation, right? So that's the first one I want. And let me put on the second one as well, and we'll formulate both of them at the same time. And the second one I want to formulate is ML in. And let's say it's for different invariant condition. Let's say it's another concrete invariance, which is about a one-way breach property. So that will be invariance 1 and 5, and about invariant preservation. So these are the 2, right? And what about the hypothesis? It's going to be a giant hypothesis as we did for the guard strengthening proof obligation. AIJH, right? Just remember this. And if you go back to where we were for the guard strengthening sequence AIJH. So they should be exactly the same. So what I would suggest is I'm going to just copy this part over here. This part is exactly the same, right? Remember, we got the axiom, we got the abstract invariance, we got also the concrete invariance over here, right? So these will be exactly the same as before. The only difference is now the only difference will be in the goal, we are going to put the concrete invariance in the post states. That's what we're going to do, right? And also for the concrete guard, I'm not going to copy and paste. I can just repeat it on the separate page. Let's go back over here. All right, let me simply paste this giant hypothesis over here. Let me make it even smaller over here. Right, you can see we got axiom, we got abstract invariance, we got concrete invariance in the pre-states, and we also need to put in the concrete guard for this ML out in this case, right? But let me also make a copy of this into another sequence as well, right? They share the same hypothesis basically, right? So hopefully this copy and paste process, which I'm showing you here, just to show the commonality between the two sequences over here, right? So let's now see the difference over here. Right? It'll be very important. And what about the concrete guard? In the case of ML out, so if we want to specify the concrete guards, let's look it up. The concrete guard for ML out is exactly over here, right? So I'm gonna put A plus B less than D, C equals 0, right? Turnstile over here. And what about the concrete guards for MLN? For MLN, the concrete guard is simply just C larger than 0, right? So that will be, let me just box better. So that will be C larger than 0. C larger than 0. And turnstile. And what about this part over here? It's going to be the key thing I would like to work out together with you. Okay, so this part over here, let's see exactly how we do it. Okay, and let me try to this will be the final answer I will put, but I want to show you the intermediate process of deriving it. Right, so let me call this star. Okay, this will be star star. Right, so the idea would be this will be the concrete invariance in the post states. You can also go back to the earlier part about the informal sketch for the invariant preservation. We actually said it should be the concrete invariant condition in the post states. Let's talk about in this particular case over here. And of course, it really depends on the effects of the abstract events, the abstract version of ML out or ML in, depending on which one you're talking about. Right? Let me also annotate this. That's also quite important. This part over here, just remind you, this part here is really the effects of the abstract version. Effects of the abstract version of the events. Depending on whether you're talking about ML out or ML in, right? Oh, sorry, ML out over here or ML in over here. And what about F, right? F is also something we spoke about earlier when we talk about the formal components. So this part over here is the effects of the concrete version of the events, depending on which one we're talking about. Basically, the effects over here is going to be used for substitution, as we did it. As we did it before. I'm pretty sure we did it earlier when we talked about invariant preservation for the abstract model, but let's do it again. Right, so let's now do the first one here. The first one over here. So it's going to be, let me put a star over here, right? For the star. The concrete invariant we are talking about is invariant number 4, right? So we want the invariant number 4 to be satisfied in the post states. So let me write a prime for the post states. It's going to be A prime plus B prime plus C prime is equal to N prime, right? However, what really appears in the final answer over here can only be the pre-state evaluation. It cannot be the prime. In order to really substitute each of the prime over here by some pre-state evaluation, we need to consider the before-after predicates, right? So let's see the before-after predicate for the abstract and concrete version for ML out events. Let's take a look. Right, so now if you look at the abstract version, we know the before-after predicate very well. M prime should be replaced by n plus 1. And for the concrete version, A prime should be equal to A plus 1. What about B and C? Don't forget. And also B prime is equal to B, and also C prime is equal to C, right? That's what we got. Let's now do it. So you can see A prime over here is going to be replaced by A plus 1. A plus 1 over here, and plus B prime is going to be replaced by B because it's unchanged. Plus C prime is equal to replaced by C, is unchanged. What about M prime? M prime should be M plus 1, right? So that's M plus 1 over here. So that'll be the final answer. Let me put it down. The final answer should be A plus 1 plus B plus C equals M plus 1. Okay, I can just make a little bit more space over here. It's equals M plus 1. Right, that's what we have. Hopefully you're following so far, right? We don't need to simplify this over here. I think that this is actually more valuable to actually see exactly what we have done in terms of the substitution. You can think about A prime plus B prime plus C prime equals M prime. And somehow for A prime, B prime, C prime, and M prime, we actually replace them by their pre-state evaluation based on the before-after predicates for the abstract and concrete version. Right? So that's the before-after predicate. And I'm pretty sure you would know how to derive the corresponding post-states concrete invariance over here for MLN. Well, but let's do it together because I know you got the other 8 different sequence that you're supposed to do as exercise. Let's do one more together with you. Okay, so that will be star star. Right? So let's put star star over here. So star star. And we are talking about invariant condition number 5, right? Which would be this one over here. A equals 0 or C equals 0. So now we talk about the post states. A prime equals 0 or C prime equals 0, right? In that case, we need to consider the before-after predicate for this particular event, right? MLN. The abstract version and the concrete version. In the abstract version, the before-after predicate, we spoke about it before, M prime equals M minus 1. And for the before-after predicate for the concrete version should be C prime equals C minus 1. And don't forget, A and B in this case doesn't change. A prime equals A, and B prime equals B, right? You can see everything actually get connected together when we formulate the sequence and later when we do the proof. Let's now do the substitution. Here, you can see A prime would just be replaced by A. What about C prime? C prime should be replaced by C minus 1. C minus 1 over here, and that's it. So overall, we got A equals 0 or C minus 1 equals 0. That's all we got. Right? So I'm going to put A equals 0 or C minus 1 equals 0. And again, I just need a little bit more space over here. All right, so that's the sequence for both, right? And so these are only 2 of the 10 sequence that we are supposed to formulate for invariant preservation. I already did 2 of them, so the remaining 8 will be up to your exercise. Please make sure you actually attempt them and make sure you can lay out in a systematic way for all of the sequence that are required for the invariant preservation for refinements. Let's now move back to the slides to see if there's anything I missed. You can double check over here. That's exactly what I just put. And exercise the remaining 8. You want to both to specify and also prove. And for these 2, actually, their proofs are in some way even simpler than the 2 related to guard strengthening. I shouldn't say it's much easier. It's not really much easier, but very similar, I should say. Right? So I would suggest the following. I don't need to waste your time by going over all the steps again, but if you really prefer me going over with you, reach out to me. I'll be more than happy to do so. But I would suggest you really need to try to attempt the proof on your own without my guidance. So I'm going to talk about those 2 exercises in a moment. Let me talk about this diagram. I will talk about this diagram in just a moment. Let me assign the exercises to you first. I want you to really try to prove this one here and also prove this one over here, right? These 2. However, I'll give you some hints, right? If you really get stuck, right, you can refer to these two clean pages as the hints. Okay, I'll get you this diagram in just a moment to conclude. Okay, exercise number 1, right? This will be the exercise for you. And as I did earlier for the first part of the refinement proof, and I already gave to you all the 3 relevant inference rule you will need in order to discharge this particular sequence, right? In some way, that's a very big hint, but in the test or in the exam, you may not be given the exact relevant inference rule. But if you want to treat this as a simpler exercise, that's okay. You can go ahead. But if you don't really want to look at these inference rule, you want to decide on your own, that's fine too. And exercise number 2 is about the second one. Okay, the exercise number 2. So I also put exercise over here. Okay, so that'll be the second exercise, actually. Okay, so exercise. All right, the final thing I would like to talk about to conclude this topic about invariant preservation, we didn't need to spend as much time simply because the proofs are very similar to what we did for the first part related to guard strengthening. And also, we already spoke about invariant preservation, the insight and also the formulation earlier in the lecture when we talk about the initial model invariant preservation. So that's why we didn't need to spend as much time. Hopefully, you can actually connect everything together. I would like to conclude this part of the lecture by using this diagram. And this diagram here is really similar to essentially the same thing as what I did earlier about the transition for concrete and also abstract. Let me show to you over here. Remember this diagram over here, right? The only difference is here I gave you very specific values for the example just for your intuition, right? But now we need to generalize our examples over here to really see what will be the general case to be proved for refinements, right? That's really the difference, right? Just always remember this is a very important diagram which we spoke about much earlier. Okay, let me go back to this diagram here. I only want to highlight a few things and then we are done for this part. Okay, and this diagram is really trying to say the following. We want to say each concrete state transition, which is over here, is simulated by an abstract state transition correspondingly over here. Okay, so what you want to think about is this part over here is a concrete state transition. Okay, let me just annotate it. So this part over here is really a concrete state transition. So think about what I'm doing now is to really put everything that we have said so far in this week together, right? And also this part over here on the top is the corresponding abstract state transition. But we want to make sure before and after each transition, there's certain constraint that will be satisfied, which I'll talk about. All right, so this will be the abstract state transition. Abstract state transition. Right, you can think about this part over here is the pre-states. Right, so this part over here is the pre-states for both concrete and abstract state. So this part over here is the pre-state for the transition. Pre-states, actually. This will be the abstract pre-states, and this will be the concrete pre-states, right? I don't need to write it down. You already see what I mean. And this part over here is really the post-states. And obviously, this will be the abstract post-states, and this will be the concrete post-states, right? And how are they related? Number one, what we did in the first part of the proof for refinement is we want to make sure the guard for the concrete events is enabled, means that the abstract guard is also enabled. So that's what we said, the concrete guard should really imply the abstract guard, or alternatively we want to say the concrete guard is stronger than the abstract guard, right? That's about the first part we did already. And we want to say that these two states are actually related by the concrete invariance in the pre-states, right? That's actually in the hypothesis in both the first part and second part. It's really important for you to realize that. Let me also try to do that. So this part over here is the concrete invariance in the pre-states. So this part over here is really the concrete invariance. Concrete invariance satisfy at the pre-states. You can see for both variable lists, the abstract variable and concrete variables, we don't put a prime, right? And given that the concrete event is enabled, it entails that, it implies that the guard for the abstract event is also enabled. So you can think about simultaneously we take the concrete transition and also we take the abstract transition as well. And now we arrive in two states, two post states, the abstract post states and also the concrete post states. And we have to make sure that the concrete invariance, the same concrete invariance will still be maintained in the post states, right? That's what we want to make sure. That's exactly what we're proving in the second part, right? So this will be my final mark over here, right? So this part over here, especially you want to see, we actually got prime over here. That's so important to notice the syntactical notion over here, right? So this will be the concrete invariance. Invariance satisfy at the post states, right? So important to see pre-states and post states, right? Really try to study this diagram very carefully together with the transition example we did much earlier, right? And that really summarizes what we really meant to communicate to you for this week, right? Alrighty, let me go back, and that's about the diagram. And of course, you will try to do the proofs and try not to look at the solution in the later slides, right? I'm not going to show you in the video, hopefully, right? I also got the proof summarized in the notes. So you definitely got a solution ready. But I would suggest really try to prove this one over here and this one over here on your own. If you really get stuck, try not to look at the solution. You can come to me and tell me where exactly you got stuck, and we can talk about it. Try to do this earlier rather than just shortly before your assessment. Alrighty, we got the final part to cover for this week, which is about how to prove initialization in the context of refinement.